All right, let's begin. So just a quick recap on what we have studied on Monday. So we started with an experiment showing that with a simple interactive sum calculator that take only integer value, we get the precise solution of the sum of these integer values. And then we proceed to try to allow user to input real numbers where it will be stored as a float type in Python. And what we get is that the sum of 0.1 plus 0.1 plus 0.1 didn't give us the precise calculations that we want. Mathematically, it should be 0.2, but 0.3, but we get something that is larger than 0.3. And then we check, does it work for all floating point numbers? It turns out for some floating point numbers, such as 0.5, it still gives us precise calculations, which is 1.5 here. 0.5 plus 0.5 plus 0.5 gives us 1.5. So we proceed to try to understand how these numbers are being represented. Okay, so we start off with integers, where integers represented in base 2, where in base 2 means that every digit is either 0 or 1. So everything that is stored in computer is either 0 or 1. So when we want to convert an integer from base 10 to base 2, we need to write in the form of sum of powers of 2. Okay, and then we proceed to understand how do we extend it for floating point numbers, those with decimals. So those are the ones that for which we have a decimal point, and everything before decimal point still work the same as in integer binary base 2 representations. Those that after the dot also work similarly, where it's also sum of powers of 2, where now the exponent is of negative exponents. Okay. Now with this, we try to understand what is the binary representation of 0.1? So we try all possibilities. So it can either be 0 or 1 for each of the position after the decimal points. And we realize that no matter what number that we put, it will always be very close to 0.1, but not exactly 0.1. In fact, we get a certain patterns of binary representation of 0.1. So in fact, we can also prove that there does not exist a finite representation of 0.1 in base 2. Okay, what we can get is something close to 0.1, but not exactly 0.1. And hence, this explains why when we do calculation of 0.1 plus 0.1 plus 0.1, we get a non-precise answer, which is not exactly 0.3, but something close to 0.3. Now, on the other hand, 0.5 can be represented precisely. As we can see here, 0.5 is represented exactly like this, dot 1. Okay, so with a binary base 2, it will be dot 1 and the rest are 0. So we know that because 0.1 can be represented precisely, there will be no rounding off error. Okay, and we have also learned how to convert binary numbers and integers using the built-in functions int or bint. And we have also seen that there are other base representations, not just base 2. Base 2 is used often this is what we represent in computer everything stored in binary 2. But when we, for example, use it to shorten the string, we can also use base 16 representations. So in this case, 1010 is represented as A. So it's just one character instead of 4 digits. Okay, so this is quite often used in IP address, in a color encoding HTML document as well. So just for your information. Now, when do we decide how to use float or int? We know that there is a trade-off. Okay, if you want a precise calculation for floating point numbers, you can utilize the decimal library, which will store the numbers in a different way so that it gives us calculation that is precise. Now I want to mention this a little bit. So when I say that when I want this to be stored precisely as 0.1 so that there will be no rounding off error, I put this as a string first and then sort of typecast it into decimal. Okay, so this will give me a type decimal that will give me no error. When I do decimal 0.1 plus decimal 0.1 plus decimal 0.1, it will give me decimal 0.3, a precise calculation. In comparison to before, 0.1 plus 0.1 plus 0.1, it will not give me precise calculation. This is of type float, and this is of type decimal. Now, I want to bring your attention to this. If I don't, decimal can also take int value, not just string, okay? But if I do that, so let's see what is decimal 0.1. Okay, first I need to import first. You see, decimal 0.1, where 0.1 is a float, okay? 0.1 is not a string, this is a float. So when 0.1 is stored in the computer, it's stored in this. It's stored as this. That's why I say it's imprecise. 0.1 cannot be stored precisely as base 2. So when it's stored in base 2 with a finally many digit, it's stored as this number here, which is a number that is close to 0.1, but not exactly 0.1. So when you typecast it, you actually typecast this string here. Okay, so in other words, you didn't get a precise representation of 0.1. So if you do 0.1 plus decimal 0.1 without first putting it into string, you are looking at the same calculations of 0.1 plus 0.1 plus 0.1. Okay, so you will get the same as this. Basically, you store this as float, right? So it will be imprecise. It will be stored as a 0.1 something something something, which is not exactly 0.1, and then only you typecast it. So what value you store is still a floating representation of 0.1 that is imprecise. So if you want precise calculation, make sure that you type it as a string, okay? You typecast it the string, not the value itself. All right, so this is very important. Now, and then we ask, why don't we always use decimal in that case? Because it takes time to compute when it's a decimal type. So if you compare this is of type float. The time is 9.3 microsecond. And if you compare this where this is of type decimal, and it takes 34.1 milliseconds. So if you want fast calculations, you might want to consider using float because it's fast, and it gives me slight error that you might want to accommodate. It's fine to have a slight error, for example. And here we give a solutions for the interactive sum calculator where everything is in decimal. And of course, you can extend it to any value. So it doesn't have to be with just 3 values. You can be any value. So this is homework to do. So extend above code to any number of inputs. All right. So you can extend it. So the idea is the same. You have user input a number, which is already of type string, which is exactly what we want. Remember, if you want it precise, it has to be of type string, and then you typecast it to decimal. Then the value that value that is being stored now will be of type decimal. That will be the precise definitions of the numbers that user enter. Okay. Now we look at some of the use cases for which we need to decide whether we want accuracy or whether we want efficiency. So the first case, say for quiz in this course, all points are either integers or with decimal 0.5. Okay, so sometimes the points is 0.5 for one question, or we deduct 0.5 for minor errors, but we kept everything either 0.5 or some integers. So the only possibilities are either 0, 0.5, 1.0, 1.5, all the way to 5. So for this case, we are also dealing with floating point numbers. We have decimal values here. So which one should we use, decimal or float? So we have 0.5, and we know that 0.5 can be represented precisely. So the solution, okay, 0.5 can be represented precisely as float. So we will just use float, okay? We don't have to convert it to decimal when we do calculation involving your quiz scores, okay? If you want to add a sum of all your quiz score, for example, we don't have to convert it to decimal first. We can just type it. You can just take the sum of all these values directly as float, because 0.5 can be represented precisely as float. There will be no routing off error. Okay. Now, on the other hand, consider a library penalty system. So suppose 1 day late of returning a book will result in a penalty of, say, 10 cents. Okay. And you are asked to build a program that keep track of the penalty cost. So for this case, we are again dealing with floating point numbers, which is 10 cents per each day the user returned the book late. So now we need to ask, when we deal with computation regarding floating point numbers, should we use decimal or should we just use float? Noting float will give us might give us routing of error. Decimal, on the other hand, will give us precise calculation, but it's slow. So again, what is the trade-off? Do we want accuracy versus efficiency? Now, for this case, when we come to money, when we come to cost in bank, for example, we want to be precise. Okay, in this case, we would want, so 0.1 cannot be represented precisely using float, and hence might give us a routing of error. So when it comes to, money or cost calculations, we often want a precise calculations. Okay, we often want precise calculations, and so we might want to opt for, we might want to use decimal in this case. Okay. So we might want to use decimal in this case because we want a precise calculations. So when you are given when you are asked to build a system, so you look at your system, what is the numbers that you deal with? If the system that you deal with always deal with integers, then you don't have to worry about whether using decimal or float, because integer gives us precise calculations, it's fast, and there will be no routing of error. But if you involve floating point numbers, then you need to stop and think, what is this floating point numbers that you are dealing with? For different cases are different. For quiz, for example, I purposely choose 0.5 because 0.5 can be represented precisely. So I didn't give like 0.1 point or 0.2 point or so on. I just give 0.5 because it makes calculation faster and it can be represented precisely. There is no ambiguous. There will be no student coming to me say that, her calculations using Python is different from what I calculate. There is no such thing because everything will be precise. That's why when I created the grade point system for quiz, I only accept 0.5 as one of the decimal for the points. Now, if you have a system where you need to deal with floating point numbers that will not be able to represent it precisely in base 2, that's where you need to start to think, do I need to use decimal? Or should I accept the fact that it can give you small error? So it really, really depends. If you're dealing with money, you might want to use decimal to give you precise calculations. Okay, so are there other ways to avoid this? So there are other ways to avoid using decimal, because decimal is slow. One way is that to avoid using float by converting it into its corresponding integer value. For example, if you have dollar in dollar, say $1.5 means $1.50. Instead of using 1.5, you can convert it into its corresponding number of cents in integer. Okay, so for example, here I have $1.1, which means $1.10. So this is in a floating point, and this is 1 plus 0.1, and 0.1 cannot be represented precisely as in base 2. So we know if you work on this 1.1 value here, you might not get precise calculations, you might get routing of error. So this is where you think, okay, in that case, I can convert it into its corresponding integer by changing the unit from dollar to cent. Okay, so $1 is 100 cents. So it will be 100 plus 10 will be 110 cents. Okay, so it will be 110 cents. Right, so now these two represent the same amount. $1.10 is the same as 110 cents. What you have changed is this unit, okay? From $1.1 to 110 cents. And what you have changed is from floating type to int type. What you did is that when you do computation using the amount cent rather than amount dollar, because now amount cent is int, everything will be precise. There is no rounding of error. Okay, so this is one thing that you can do, is to change the floating point type to its equivalent integer type. All right. So now amount cent will be of type int, and you have no problems with float. Now, how about the other cases, for example? So another example, say 1.5 hours. Okay, so 1.5 hours is the same as 1 hour and 30 minutes. And this is floating point type, 1.5. Okay, so this 1.5 it's not going to give us an issue because 0.5 can be represented precisely in base 2. However, I want you to practice how to convert this number to its corresponding integer in a different unit. So for each hour, you have 60 minutes. Okay, so I have 1 hour and 30 minutes here. So it will be 60 minutes plus another 30 minutes. That will be your 90 minutes. So this will represent 90 minutes. So they both represent the same amount of time. 1.5 hours is the same as 90 minutes. Now, the difference is that this is dealing with floating point numbers and this is dealing with int. And we love to deal with int because everything will be precise. Okay? Now, that's the idea of how to convert float, how to avoid float by converting it to a corresponding integers. Now, in the lab, you will have a chance to play around with this, with the library system that we have shown. Now, before we proceed further, I have one thing that I want to mention regarding the lab. So at one point, when I talk about, in the presentations, when I talk about this part here, file system 4, where I say the maximum file is kept at 20. So during the presentation at this part, I made a mistake where I use mat.ceil here instead of mat.floor. Okay, towards the end of the presentation, I noticed this error and I already fixed it. So when you read it, when you watch the video and you find that something is wrong with this, so just keep on going towards the end. I will correct it towards the end. Where at the beginning I put mat.ceil, it should be mat.floor. Okay, but the rest of the things should be all right. All right, just to give you a reminder, just in case you find it confusing at this part here. Okay, now another thing is that you can use decimal or fraction. We didn't do fractions, we only do decimals here. And you can also use other problem-specific library for certain algorithms that will know numerical properties. For example, if you want to solve differential equations, there are other libraries that are available with specific algorithms that solve differential equations. So you can use those specific library. And you can use, for example, symbolic computation in computer algebra system instead of a programming languages. So note that programming languages is very wide. You can use for all those tasks. But if we want to do mathematical computations, such as solving differential equations, finding the finite field, finding the ring, etc., you might want to go to other algebra systems, such as Magma, Mabel. So example, so Magma, Mabel, Sage. These are deal with symbolic computations, where we take variable as it is, and it can do a lot of other computations for advanced mathematics as well. And also, one more thing, when using float, you never want to compare for equality. Okay, so you don't want to compare, for example, whether 0.1 plus 0.1 is equals to 0.3. When dealing with float, you don't do comparison using equality, but you compare by checking whether they are close to each other. Okay, so instead, check if they are the two values that you want to check, the two values that you want to compare are close to each other. Okay, instead of checking precise equality, whether they are equal, you don't do that because you know for float there will be routing of errors. Instead of checking of that, you check whether they are close to each other. So how do we do that? So instead of checking A is equals to B, this means checking equality where A and B are float numbers. You check whether they are close to each other by checking the difference between them. And it's not just the difference, but the absolute difference. Okay, that means if A is greater than B, so let's talk about absolute here. So absolute is a function that takes a number and return the absolute value of the number. So what is the value of the number? So the absolute value of negative of, say, so example, absolute of -1 is 1. That means you remove the negative. So it always positive. Absolute of 1 is just 1. So absolute basically convert a number to its non-negative. Okay. So there's an example. So you want to check the absolute difference between these two values, whether they are less than a small number, a very small number called epsilon. Okay. So here's example. Instead of checking, so 0.1 plus 0.1 plus 0.1, you don't want to check whether this is equal to 0.3 because this will be false, even though we know mathematically speaking, it should be true. So instead of doing that, what you did is to check the difference between them. 0.1 plus 0.1 plus 0.1 is the value that you want to compare with 0.3, whether it is close to 0.3. Okay, you take the difference between them. Yeah, remember, this difference can be negative, but we are not interested in whether one is bigger than the other. We're only interested in the gap between the two. So we take the absolute value. Again, you can do help apps. Okay, it return the absolute value of the argument. So absolute value of a negative value will always give the positive of this negative value. So absolute will always give a positive value. Okay, whether it is less than, for example, a small number. Okay, this small number is called an epsilon. In mathematics, we like to use epsilon means small. So this depends on how accurate you want. Okay, so if this is true, which means that this number here, the sum of 0.1 plus 0.1 plus 0.1 is very close to 0.3. In fact, they are equal up to 2 decimal points. Okay, now if you want to check whether they are equal up to 3 decimal points, you do 0.001, and it's true, they are equal up to 3 decimal points. You can control this epsilon here, the value of epsilon, based on how much gap or how much error that you can tolerate. So if this is true, which means that, okay, you can tolerate errors up to 3 decimal points. Okay, so this is true, you can tolerate up to 3 decimal points. So if you say your system can only tolerate errors up to, say, 5 decimal points, 1, 2, 3, 4, 5, then you need to decrease this epsilon value to be smaller. Okay, in this case, this is still true up to 5 decimal points. Okay, so it depends on your system. Say you don't mind inaccurate results because you care more about efficiency, so you don't want to use decimal. All right, so you are fine with some little routing of errors, but you want to keep the routing of errors to be small. All right, say it should be precise up to certain decimal points. For example, 5 decimal points. So you do a sanity check whether the results that you compute with the precise calculation, is it less than this 0.0001? If it is, you are assured that the errors is precise up to 5 decimal points, so you will accept this value. Okay, so this is very important. Whenever you do with calculations with floating point numbers, you always don't check equality, but you check whether they are close to each other. Okay, so another thing that I want to point out with regards to floating point numbers is that there is an issue called loss of significant digits. Okay, let's look at this example. Say we want to compute these equations, a quadratic equation, which you should have learned. For ax squared plus bx plus c equals to 0, where a, b, and c are given. Okay, and you know in your high school, so there will be 2 values of x that satisfy this equality here. That will be x1, which is minus b plus minus square root of b squared minus 4ac divided by 2a. And another value of x that satisfies this equality will be minus b minus square root of b squared minus 4ac divided by 2a. In other words, we're finding the root of these equations, and there are two roots. This difference is, this is either the first root will be plus, the second root will be minus here. And this is our solution here. If we follow this formula exactly, say quadratic ABC. So here is something, so this is something you have not learned yet. We will learn it very soon. This is called defining a function. So we're not going to go through this at this moment. So we're going to write our own calculation. Suppose we have a equals to 1, b equals to minus 2 with 1, 2, 3, 4, 5, 6, 7, 8, 2 times 10 to the power 8, and minus 2 times 10 to the power 8, and c equals to 1 here. Now we want to find the root of this equation here. Okay, so what is the root of this equation? So x1 will be equals to this, will be minus b plus method square root. So first we need to import that. If you want to use the library, you must make sure that you import it first. Square root of b to the power 2 times 4 times a times c. Okay, and then the whole thing divided by 2 times a. Okay, this is my value of x1. This will be one of the root, and x2 will be another root. Instead of plus now, it's minus. Okay, so let's see what is this x1 and x2. We see that it says that the root of this equation here, that means the value of x that satisfies this equation is 2 times 10 to the power 8, I think, 2, 4, 6, 8. And the other root is 0. But here, second, we are saying that x1, which is 2 times 10 to the power 8, satisfies this equation. We are also saying that according to our calculation, 0 also satisfies these equations. But hang on a second. The equation that we are looking for is x to the power 2 plus 2 times 10 to the power 8 plus 1. Okay, so this is the equations that we are dealing with. All right, and what is x? Say if I put x equals to x1, it didn't give me 0. So when x equals to 2 times 10 to the power 8, okay, and I plug in the value of 2 times 10 to the power 8 to this equation here, it didn't give me that it's equals to 0. It gives me something that is a very large number. Now let's try the other one. Say x equals to x2, in which case x2 is equal to 0. Again, I plug in the value of x into this equation here, and I get 2001, which is not, again, it's not equal to 0. But according to the formula, I think I calculate wrongly here. Okay, it gives me these numbers here, and it gives me minus this number here. Okay, according to my formula, if x1 and x2 should be the value of x that satisfy this equality, that should give me 0. But my calculations from this is that it doesn't give me 0. And we try to investigate what happened. So in the future, when you work on the system like this and you see something like this, first, you will often use a formula that is given in math, in algebra. And then when you work with it, you realize that, hey, even though I follow the formula, the answer given to me is not correct. So don't just blindly apply the formula, but investigate. Whatever formula that you use to compute it, plug it back in to see whether it is the right answer. If it's not the right answer, you need to start to investigate. Is it because of how you compute x1 and x2 is wrong? Is there something wrong with my calculation here? Did I miss a bracket? Did I miss, instead of b squared, I put b times 2? You check and you see that there is no error here, then you've tried to figure out what could be an issue. If it's not because of your syntax, if it's not because of how you understand the formula, what could be an issue? So another issue that could be, it's because, again, we are dealing with numbers, floating point numbers in particular. And in this case, you are saying that, wait a second, there is no floating point numbers here. See, A, B, C here, they are integers. So our A, B, C are integers. So you didn't expect that there will be a floating point errors. However, you realize that when you do square root, and you do divide, this will give you floating point numbers, right? So you do square root of b squared minus 4ac. This is computing something that is a square root of something. It might become a floating point numbers. And you do division. When you do division of something that cannot be divided properly, you will give floating point number as well. So even though it's seemingly noted as A, B, C is not floating point numbers, but the calculation itself gives floating point numbers, and hence there must be a rounding off error. So let's play around with it. Okay. So let's say we have d equals to b squared minus 4ac. Okay, and b squared. So b is equals to minus 2e8. So e8 means 10 to the power 8. Okay, it's a short form. So b squared, which means minus 2e8 times minus 2e8, minus 4 times a times c will give me 4e16 minus 4. Okay, here, one thing I want to mention here. 4e16 minus 4 means 4 times 10 to the power 16 minus 4. This is not a floating point number. This is an int, by the way. Okay, this is a whole number, 4 times 10 to the power 16 minus 4. However, this number is too big to be stored in Python as an int. So what happened is that it's removed minus 4 from its computations, and there is a loss of significant digit here. So again, the value of d was not precisely represented as 4 times 10 to the power 16 minus 4, but it's just saved as 4 times 10 to the power 16. Okay, and hence we have the value of d here that we will use in our calculations that give us a different result. Okay, so this is another numerical computations error that you need to see. Okay, it's not just about floating point that give you rounding off error. There's another error called loss of significant digit. When a number is too big, it couldn't be stored, and so we reduce some of the digits so that it can be stored precisely in that finite number of bits. So you can change this number of bits in Python. If you want to store in 53 bits, you can extend it to 64 bits, up to you. However, if it uses the default, it can store in a certain number of bits, and if we exceed that, it will lose some of the significant digits. This is when you deal with numbers that are too big. Okay, so when d is 4 times 10 to the power 16 rather than 4 times 10 to the power minus 4, what you get is this value, minus b plus d divided by 2a. With the number, you get 2 times 10 to the power e, and the other one is 0. All right, so which is why we couldn't get the result that we want, which is why the value that we get does not satisfy the equality, even though we follow the formula exactly. This is because for these equations, to find the root of these equations, the numbers of the roots are too big. One of them is too big, one of them is too small. One is too big, there is a loss of significant digit error. Okay, so how can we avoid such an error? Again, you can use decimal for exact precision, but this is slower. All right, and however, you can also use an alternate formula. So the loss of significant digit happens in calculations of the root of the quadratic equations when the root has very big numbers and the other root has very small numbers. So mathematicians have come up with a different formula that is more numerical stable, and it's called Vieta formula. And it doesn't lead to large intermediate values. So we don't want the intermediate value, which is b squared minus 4ac, to be large, because when it's large, then you get the loss of significant digit error. Okay, so Vieta formula specifically deal with this case, which is what they call numerical stable. So this is beyond the scope. So if you're interested, go and check it out. And I just want you to be aware of such an error that could exist, even though we are not dealing with floating point numbers. Okay, so as a summary, so numbers of type float provide a reasonably good approximation to deal with real numbers. They are numbers that cannot be represented precisely. For example, 0.1, 0.2, these cannot be represented precisely in base 2. And arithmetic operations on these kind of numbers will lead to rounding off errors. So you don't want to compare for equality. So it's very important. Instead of compare whether A is equals to B, when deal with A and B are floating point numbers, you check whether the absolute difference between them is less than a small value. And this small value is up to you to decide how precise you want it to be. If you want B and A to be absolutely very close to each other, you need to make epsilon as small as possible. And of course, when you deal with lots of significant digits, you can always use an alternative formula that is more numerically stable. And this is often happens when you have a very large numbers, integers, that will cause a loss of significant digits. All right, and that's all for today. And we're gonna stop here to do the quiz.